Hey guys, today we're going to learn about electrical concepts and equations. So last time we got to see how static charges work and we learned about Coulomb's law. Now we're going to get into some of the specific tools that we use for analyzing electric circuits and electrical situations. So there's a lot of material to cover, but it all kind of works together, so it's not too bad. So we're going to learn about current, volts, and resistance. So we're going to learn about what they are, what symbols we use to represent them. And then we're going to learn about Ohm's law, which is how these three quantities react and relate to each other. And then finally, we're going to learn about electric power, which is one more equation and some combinations of equations. So first we're going to look at current, and we've seen current before, so that's a good place to start. So as you know, a current is a flow of charge. It's electrons actually going through a wire, and the units of measurement are amps or amperes, amps. And as we learned last time, an amp is 1 coulomb per second of charge. So if we look at one place in a wire and we watch 1 coulomb of charge pass that point in 1 second, then we have 1 amp. And as we saw last time, strangely, amps and coulombs are defined in reference to each other. And we're going to see why that actually is done today when we get to power. Now, taking a step farther here, another way we express this, that current is 1 amp per second. I, capital I, is the symbol for the unit. So amps are abbreviated with a capital A, but the concept of current is represented by the capital letter I. Okay, so next we're going to move on to Ohm's law, and we will define the individual parts of this in a moment, explain what they are, but this is where it all comes together, so here it is. So Ohm's law is I, which we've already seen as current, is equal to V, which is voltage, divided by R, which is resistance. Okay, so I equals V over R. Basically what this means is that if you have a given conductor with a certain resistance, that's just going to be a characteristic of the material. It is what it is, and you apply a certain voltage across that conductor. The interaction between how hard you're pushing the electrons and how hard it is for them to get through the conductor, that will result in some flow of charge. Okay, so these are the independent variables. You can choose whatever substance you want. As a physicist, you can choose whatever voltage you want to try to push the electrons through that. That's in your control too. And then the dependent variable, the current that results, well, that's the dependent variable. So this is the way that AP, College Board, your textbook presents Ohm's law. I equals V over R, because I is the dependent variable, depends on the other two. Okay, now again, we're going to talk about the specifics of what these are and what they mean in a moment, but this is how they all fit together. Now, you may have seen Ohm's law written this way, and it's much more famous this way. V equals IR. This is Ohm's law. It's the same thing. As you can see, it's just a rearrangement of I equals V over R. And this is more common because it's easier to print. It's easier to set and type. But this doesn't really reflect the relationship between these variables, which is why we go with I equals V over R in the book. Okay. Again, to define these things, and we'll explain the concept in a moment, V in Ohm's law is volts. And the nice thing about volts and the symbol for volts is that they're the same. Yay, it's the only one. I is current, as we saw before, and the units of current is amps. And then finally, R is resistance. And the symbol for resistance is a unit called ohms, which we represent with a Greek capital omega. Looks like a horseshoe. Okay, so V is volts, I is current in amps, R is resistance in ohms. So take a minute to write these things down. Now, you sometimes also hear volts as described as electrical potential. That's just what it is. I'm going to explain volts here in a moment, but this is the most common way it's described, electrical potential. Anyway, moving right along here. So to understand all these things, sometimes it's helpful to think of water as plumbing, like water flowing through a pipe, just like electrons flow through a wire. Okay, now it's not a perfect analogy, but it works pretty well. Okay, so current is like the volume of water flowing through a pipe, gallons per minute. So you could have a great big pipe with the water flowing slowly through it. You're still going to get a lot of gallons per minute, like pouring a bucket of water out on the ground. It's not going very fast, but it's got such a large opening that you have a large current, a large amount of water, a large volume of water flowing through it. Or you could have a little skinny pipe with the water going through it really, really fast. You still have the same gallons per minute. So current is like the volume of water flowing through the pipe in gallons per minute. Next we have, let's see, why isn't it reacting here? There we go. All right, so voltage is like water pressure. Okay, so voltage, electromotive force or electric potential is the water pressure trying to force the water through the pipe. Okay, so it's like water pressure. And then finally, resistance is like how small the opening is that the water is flowing through. Now, notice I say how small the opening is and not how large the opening is. Okay, so a small pipe or a drinking straw is going to allow less water to flow through than a great big pipe. So high resistance is small diameter in this analogy. Only in terms of water. Now, when we're talking about the resistance of materials, is a characteristic of a material. And yeah, the diameter doesn't come into play directly. It's mostly about what the stuff is made of. Anyway, so resistance, ohms, is like how small the opening is. So let's think about how these relate to each other. So, for example, how is water flow related to pressure? Let's looking at this big pipe here. So suppose we have a water tank here with lots of pressure in it, okay? A lot of water is going to come squirting out of this pipe. So you're going to have a high current, a large volume of water flowing through here. Likewise, if you have low pressure in the tank here, then it's just going to be kind of dribbling out, and you're not going to have a very large volume of water, so you're going to have a low current. Okay. And the way we would relate that is to say that flow is proportional to pressure. If you have high pressure, you're going to have a lot of flow. If you have low pressure, you're going to have a low flow. In the analogy here, high voltage means high amps. Low voltage means low amps, low current. Now, how about resistance? Now, if we have a constant pressure back here and a large pipe, this large pipe has low resistance. So a high pressure and a low resistance makes a high current. There's going to be a large volume of water coming out of this. Conversely, if we have high pressure and just a little skinny pipe, water's going to be squirting out of here, but not many gallons per minute. It's going to take a while to fill your bucket. So high resistance means low current with constant voltage. And here it is again. So flow is inversely proportional to resistance. And when we combine these, flow is positively proportional to pressure and inversely proportional resistance. And there you get the I equals V over R. This is the derivation of Ohm's law. Okay, hopefully that makes it a little bit more understandable. Go back and watch that part and think about it a little bit if you think it'll help. Now we'll summarize here our units. Let's see, I need to find some place to put this. There I go, hide me over in the corner here. Current is amps, and the symbol is A. Electric potential is volts, and that's in V. Resistance is in ohms, and that's omega is the symbol. Now, the concept for current is I. Voltage, again, is V. Resistance is capital R in Ohm's law. Should have had those in there, but that's how it goes. Okay, finally, that brings us to electric power. Yeah, we're doing okay on time. And I'm just going to start off here with the equation. This is for electrical power, P equals IV. And I'm going to go to the clipboard here for a minute because it's just a little bit faster than putting the stuff on slides. Now, this is power, and we've seen power before. And as you remember, power is in watts. And it turns out that electrical power is equal to current times voltage. So P equals IV. And this, by the way, is the reason that we define volts and coulombs and amps in relationship to each other, in reference to each other. It turns out when you do it this way, electrical power of watts of electrical power is the same of watts of mechanical power. which means that if you have a generator which is turned mechanically and you figure out how much mechanical power is going into that generator, you have the same power in electrical watts coming out of that generator. So you can transition from the mechanical to the electrical seamlessly. That's why they do it that way. Okay, that's a little bit behind the scenes. Let's go to our clipboard here and talk about a couple things. So first, the power equation. Power equation is P equals IV. This is power in watts. This is current in amps. And this is potential, electric potential in volts. Fair enough. P equals IV. So if we have 3 amps pushed by 11 volts, that's going to be 33 watts of power. Not complicated.